listeners, and welcome back to QuantumCast'24. Today we have an exciting episode where we'll explore two fundamental areas of physics: quantum mechanics, which has a very direct relativity to our project here today, and of course, nuclear physics. Joining with us today to unravel these very interesting topics is Professor S.R.D. Rosa, a member of the management board of the Sri Lanka Atomic Energy Board. Thank you, Professor, for taking our time off your heavy schedule and being here. Alright, sir. Before we dive into physics, of course, we'd love to learn about how your personal life and your personal journey has been so far. So, sir, would you mind explaining to us and sharing with us how you first came into interest with physics and the subject as a whole?
Okay, thank you so much for inviting me. So the answer to your question is actually, my hometown is Sidua. I went to a very small school. Then after that, I think I passed the Year 5 scholarship. Then I went to Central College. So I did my O-levels in 1971 or so, I don't remember now. So even from those days, I think I was a little intelligent. Not very, very intelligent, but say a mediocre guy. So even my parents learned that I'm sort of a little above average person. So then, because those days actually we were separated into streams at year 8. So we had to select what type of stream you want to proceed forward. That is for science or math for science, commerce or arts. So we started our career actually at year 8. So starting from year 8, we learned chemistry, physics, biology, advanced maths, applied maths, everything, because that was the era. So after that, of course, after several years later, now we have this common O-level exam. But we did sciences starting from year 8. So then after passing the O-levels, actually I want to do physical science. I want to get into physical science stream. And then after that, I came to Columbia University in the science faculty. And then after the first year, I was selected to do physics special. Because those days actually special degrees were selected after the first year. Now it's after second year, after 2 years. So in our batch, we had 6 students who did physics special, or now we call physics major in terms of sort of American university standards. It's called the physics major. So then after that, I got a first class. Then I was absorbed to the faculty. Those days actually we didn't have too many lecturers, so even some lecturers came from abroad. So our batch actually, one of my partners is Dr. Sarath Gunapal. Now he is at NASA. Then 3 of us got first class. That was actually a little different at that time. Now of course students are getting first classes, but those days first classes were very rare. So for some reason, actually 3 of us got first classes out of 6. So we went to do our further studies, postgraduate studies to USA, University of Pittsburgh. Actually, Dr. Gunapal and Dr. Karunasiri, they went early because they didn't want to stay in Sri Lanka. Even from at that time, they said, no, we don't want to. Because even at that time, there were enough vacancies in the university, even they could have get into the assistant lecturer position. But I said I was a little different. I don't know why. I wanted to come back to Sri Lanka, so I took leave from university. So I went to USA after serving 1 year, because straight away they don't release me. So now at the moment, as you know, Dr. Gunapal is at NASA, and Dr. Karunasiri, one of my other batchmates, is Emeritus Professor at Naval Academy in San Francisco. So after my PhD, I came back to Sri Lanka. It was in 1987. So at that time, universities were closed actually. So I thought of going back also, but luckily or unluckily, I didn't go back. because universities were closed for several years, as you know, we had problems in the country. So that's how I started my life. So after 41 years, 6 months service, I got retirement because once you come to age 65, you had to retire in the university. So and after that, I became the chairman of Atomic Energy Board. So that's the short description of my career.
Thank you so much, sir, for giving a brief run-through of how your life has been so far. It seems very obvious that all of your hard work so far has paid off, because you have received a very prestigious position within our country, and you've become a part of the Sri Lanka's Atomic Energy Board, which is a very prestigious place to get to in life. So, sir, would it be okay if I asked you to define some of the key moments or challenges you faced along the way of reaching your great milestones?
I never got any challenges. So actually, I am a very simple guy. Throughout my life, actually, I don't know. I never had any challenges. Everything went smoothly. Even my family life, I got a very good wife. I sailed through without any problems. So even in the universities, actually, all the students of mine, they like me because I can teach well. Because those days, when you want to get the appointment or when you are recruited to the university, nobody checked us whether we can even speak, whether we can even teach. So they gave the position only because of the academic merit. Nowadays, of course, we always, once you recruit assistant lecturer, he has to go through education part and education courses. We check their ability to whether he can at least speak and at least smile, at least he can teach. So I never had any sort of nothing to grumble. So everything went smoothly. So after that, actually, since my PhD is on nuclear physics, I did nuclear physics back then, 1980s. So our university had a tandem Van de Graaff accelerator at that time. So I have worked in some other accelerator facilities as well. I could have stayed in US because even my advisor asked me to stay, but really I wanted to come back. Even my wife said, let's go home. I don't repent on that decision, because I have taught a lot of students. Now they are back in US. Of course, they don't come back, but it's all right. I mean, as long as you are happy, and as long as you are happy with what you are doing, whether you are in Sri Lanka or in abroad, it doesn't matter. Because if all these PhD holders, if they come back to Sri Lanka, of course, we don't have occasions or opportunity to offer their jobs. So I have a lot of students who are in states, in Germany and so on, maybe around 4,000, 5,000. So I am a very satisfied person. I always smile. I always enjoy life. I have never felt any challenges in my life. So that's the short story. Actually.
Thank you, sir. It seems very interesting to hear how you haven't gone through challenges and yet you've come to such a great position in life. Sir, would you mind me asking how, essentially speaking, what advice would you give to students who are chasing a life within physics as a whole? What sort of advice would you like to give for these students?
So my advice to any students is enjoy what you do. Whatever you do, you have to enjoy. If you don't enjoy what you do, I mean, there's no point of doing it. So now, for example, I always love to teach. That's the main reason I want to come back to Sri Lanka. Because if I didn't do very well in the exams, still I would be a physics teacher, because I like to teach. So that's my passion, and I enjoy. So even even today, when a school asks me to come, and I always go and give a lecture. So when I look at young people's faces, I always enjoy. So my advice to young children is think of what you want to do in your life. Have an aim. Sometimes you might not get what you really want, but still what you do in life, even your job, you have to enjoy. So don't grumble, because there's nothing to worry in this life, because we live in only very short time, maybe 8 years, who knows. So if you enjoy what you do, even learning should be enjoyment. So if you love physics, please do. But there are a lot of ample opportunities in the world for students who are doing sciences. Sometimes students have this wrong idea. You have to do engineering and medicine to come to the top. No, that is not true. But there are so many examples that I can give you. Even by doing sciences, you can come up to the top. Because if you want to find out new things, if you want to do research, if you enjoy of finding things out, then of course you all can do physics, chemistry, biology, mathematics. So the world is very open. World is like a global village. So if you do very well, there are ample opportunities in the world. Whether you want to go to US or Germany or wherever, you can do very well. So sometimes when you do sciences, sometimes you can contribute a lot rather than becoming engineer, because sometimes when you become engineer, you are sort of geared, or you are doing a very small area. Even today most of our engineers they do a lot of administration work, not really the engineering. So my advice to students is, as I told you at the beginning, have an aim in your life. Try to achieve that aim. Even if you don't achieve that aim, don't get frustrated. Always I tell students, do your best and accept what you get. That's my motto in life. Do your best and accept what you get. What else you can do in life? But you have to work hard. You have to do your best and accept what you get.
Thank you for that amazing advice, sir. Because now I feel like majority of the students in society want to go after a job that gives them more money instead of what they actually like to do. So yeah, advice I feel like is very useful for lots of people within Sri Lanka and out of Sri Lanka as well. Thank you so much, sir, for that amazing idea. And of course, sir, thank you for sticking with Sri Lanka and giving Sri Lanka an opportunity and a chance. Because without you, I don't feel like Sri Lanka would have been able to have such great students and have much more inspiration. And thank you so much, sir, for sticking with Sri Lanka.
Okay, thank you for your kind words.
Welcome to NCHS.
Studying has never felt this good.
It's not just studying.
This is what a lab should be. Whatever I want, whenever I need.
I don't miss a single class of it.
I'm flying to Australia next week.
Commence degree pathways at NCHS and continue in Australia, Malaysia or USA. Unlock your future.
Alright, so with that, now that we have a rough idea of who you are as an individual, let's move on to the actual quantum mechanics field of today. And so, sir, within shifting our focus to quantum mechanics, Professor Rosa, could you explain to us what quantum mechanics is with a basic run through and why it's so important to us as individuals?
Yeah, actually now, when you study physics, we had different eras of the developments. So normally the Newtonian mechanics. That's what you normally learn when you are in the A level, either in mathematics or physics or even engineering. So, but in the latter part of beginning of 20th century, at the end of 19th century, scientists have found that when you want to study small things in the universe, say atoms, molecules, particles, the Newtonian mechanics, the rules of Newtonian mechanics badly fails. So that's how these quantum mechanics developed. Actually, always science is like that. If you could explain everything from Newtonian mechanics, then nobody will develop any other mechanics. Why you want to develop something else if you can explain things that you know of? So, but scientists have got a lot of evidences. I don't have enough time to go through that. When you come to the smallest things in the world, things look different. Things don't look like this so-called this macroscopic world. Because now when we talk about engineering or physics or whatever, we deal with machines, vehicles, lorries, cars, buses, we say they are macroscopic. But we all know they are made out of atoms and molecules. Of course, we don't see them from our naked eye. So when you come to these small scale things, nature behaves rather differently. So that's how actually quantum mechanics developed by scientists, because of the reason that they were unable to explain. Science always has that theory, because if you are unable to explain something from your known theories, then you try to modify the theory. First you try by modification. But if that fails, then you have to think of new thing, a new model. Even in our life is like that. If you can't understand a person from the things that you know, we are happy. But if you can't understand the person with the things that you know, then we have to think differently. That's what even maybe you might, I don't know whether you all can understand your parents. So that's how you understand your parents, from the known facts. If you can't understand, then maybe your fiancé or girlfriends or whatever, then you want to act differently. So that's how life goes. So if you can explain the things from the things you know of, then you don't have to worry about it. Why take all the trouble? But as long as you find that you can't explain things from the known things, and then they have to think of new ideas. So that's how quantum mechanics sort of emerged from scratch. So even the quantum means actually discreteness. When you come to small things in the world, they are discrete rather than continuous. Now if you look at, we are made out of molecules and atoms. Of course, we don't see them, but they are discrete things. So using discrete things, you can develop or you can make macroscopic world. So there are major differences when you come to classical mechanics or Newtonian mechanics, as we say, and quantum mechanics. So of course, one of the major differences, if you think of energy, angular momentum, mass and other things, when you come to small things in the world, they are discrete. I can give you a simple example. Now if you take, say, water. If you take some water, we think mass of water is continuous. But we know water is made out of water molecules. So if you take a drop of water, there are a large number of water molecules because Avogadro's number is large. Just think that the mass of water molecule happen to be 1 kilogram. Just think. Then our size will be very different. Just think we have not changed. The mass of one water molecule is 1 kilogram. Then how do you drink water in 1 kilogram packets? So you can't get 1.5 kilograms, right? Because it's water molecule, either one water molecule or two water molecules or three water molecules. So then you have to drink water in 1 kilogram packets. So you can see the discreteness. Now, in the day-to-day life, we don't see that. Why? There are two reasons. First reason is the mass of water molecule is very small, but 10 to the minus 27 kilograms. So, we can't measure it from our normal instruments. And the other thing is, Avogadro's number is so large, even if you take a small drop of water, there are millions and millions of water molecules. So, therefore, the discreteness is washed out in the microscopic world. And actually, it's always say nice. Even if you think of our skin, we think it's nice and smooth and continuous. But if you go and look through a microscope, you will see the discreteness. If you have a powerful electron microscope, you will see more further details. So you can see the whole universe is made out of small entities. So therefore, the quantum mechanics, one of the rules, basic rules of quantum mechanics is things are discrete. Even charge is discrete. Now, if you charge the object, sometimes we say you can get n number of coulombs. No, that is not true. Charge has to be n times charge of an electron. For electronic charge, you can't divide. Of course, now you have these protons and neutrons are made out of quarks, but electron charge is the fundamental charge. So therefore, if you charge the object, say the charge is capital Q should be equal to n should be an integer, times the charge of an electron. Even if you take water, actually there is a formula for mass of water. Mass of water, capital M, is n times mass of individual water molecule. So n has to be an integer, right? So in day-to-day life, you add n to n plus 1, macroscopic, well, there's no difference because the things are very small. So the basic concept in quantum mechanics is things are discrete. Even the word quantum derives from that. Quantum of money. Now money is also discrete. Now we can't get any amount of money. No? Now nowadays maybe when we were small, even 5 cents is worth. You can even buy something for 5 cents. Say 1 cent, 2 cents, 5 cents, 10 cents. So they are discrete. We can't get 1.5 to 3.5 like that, because the money is also is quantized, discrete. Even say if you think of members in a family, it's quantized. Either you have no children or one child or two children, like that. So some things in the world are actually discrete. So like that, the basic idea, one of the basic ideas of quantum mechanics is things are quantized. So they are discrete in the sense. So then the other major issue in quantum mechanics is quantum mechanics always talks about probabilities, not certainties. That is the basic difference between classical mechanics, Newtonian mechanics, with the quantum mechanics. Because now say according to classical mechanics, we say time t equals 0. This bus is here. After time t equals t, bus is somewhere else. But in quantum mechanics, we say there is always a probability of finding the bus at that point. So according to quantum mechanics, the world or the nature is probabilistic, not deterministic. I mean, nothing you can't exactly make sure this happens or not. If you consider electron in an atom, now normally you draw circles, no? So that is a wrong idea actually. For a small kid, all right. Actually, electrons won't travel with this along the same orbit all the time. They are called orbits. Now scientists have found it's not an orbit, it's orbital. Takshika, we call it, not Kavacha. So there is always a probability of finding the electron. The maximum probability is at that what you call the orbit. Because scientists have seen when you go to heavy atoms, the proton can capture the electron. It's called electron capture. So if the electron is orbiting the same circle, how come the proton can capture the electron? So there are instances actually protons can capture the electron and the proton becomes a neutron and neutrino is emitted. So according to the quantum mechanics, always you represent things, say probability, using probabilities. Not so even in our life is like that. We don't know what will happen tomorrow. I might die tomorrow. Who knows? When you cross the road, probability is not 0 that a bus comes and hit you, right? But maybe you might say tomorrow the sun will rise. That's not probabilistic. It is deterministic, right? Say my wife not will leave me. That is definite, right? So there are things in life like that. But if you look at day-to-day life, or even if you look at the things psychologically, we always talk about probabilities. Now you also don't know what you all are going to do in future, right? You might be an engineer, doctor, scientist, lecturer, businessman, who knows? So there is always a probability part attached to quantum mechanics. That again comes with the waves also. Because according to quantum mechanics, all the particles are represented by waves, not as particles. So even that's why when you study chemistry in your A level, you draw orbitals. So the orbitals are actually the probability distribution. So at some places, electrons will like to be at that point more probable. That's where the bonds can be formed. Some places electrons you can't find. So it's a probabilistic nature, probabilistic distribution. So nature always goes with probabilistic nature rather than determined. That's the difference between quantum and Newtonian classical mechanics. So the same reason is, when you think of a wave is not localized. Now when you say particles are localized, now you are there, right? But if I represent you by a wave, then you can be in this room anywhere. So even sound waves, that's why you all can listen to me or hear me, because they are not localized, they are distributed. So always quantum mechanics, we represent particles by waves and we attach a wave function mathematically, all the wave function, right? So that's what you learn in your A-level chemistry. Actually, you draw the probability of finding the electron. So if they are particles, they have a definite orbits. So that's not true. So if you go to small things in the world, particles also behave like waves. So that is also one of the major foundation or major thing that comes in quantum mechanics. So things are discrete. It's not deterministic. It's always goes with probabilistic, and you represent particles by waves.
Welcome to NCHS.
Studying has never felt this good.
It's not just studying.
This is what a lab should be. Whatever I want, whenever I need.
I don't miss a single class of it.
I'm flying to Australia next week.
Commence degree pathways at NCHS and continue in Australia, Malaysia or USA. Unlock your future.
Thank you, sir, for those very interesting concepts. I'm starting to get more interested in quantum mechanics now as well. This is very exciting. Alright, sir, with that, we'll be moving on to our next question. So, sir, I've heard that within quantum mechanics, I have heard that particles are very unpredictable and they can exist in multiple states as once. So, this seems like a very intriguing concept. Do you mind explaining how that system works?
Yeah, actually, as you said, it's a very difficult thing to understand because that is against our normal intuition. So I can give a simple example now. Say if you throw a coin, now in a cricket match you have to throw the coin to find out. So once you throw the coin, actually it comes and falls on the ground. So it should either tail or head. But while it is in air, what can you say? So it's very difficult to answer that question. When it is in air, it can be either tail or head. So as soon as you observe, in quantum mechanics we say when the system collapses. So therefore the one when the coin is in air, we say it's a superimposition of head and tails. Both are there. But as soon as it comes down and lie on the ground, fall on the ground, then only you see either tail or head. So quantum mechanics is like that. Actually, the reason being that actually quantum mechanics is wave mechanics. But as I told you earlier, in quantum mechanics we represent all the particles by waves. We don't treat them as particles. That's a scenario in life. We have particles, matter and waves. That's like a symmetry in nature. Now we say we are matter. We never say I am a wave. Right? But when you go to small things in the life, it behaves like waves also. That's what scientists have found. What to do? That's the nature gives us. So that's called the wave-particle duality. Duality means you have two lives. Right? Sometimes you behave like this. Sometimes you behave like that. Even human beings are like that. Human beings can't be predictable. No? One of the most difficult thing in world is try to understand people. Because they change with subtle things. We change with the environment. They change with the neighborhood. Right? We change with the people living around you. So the reason behind this the superposition actually because of the wave. Because you all know, I think you all have learned in your A-level, waves can be superimposed. When you have an incident wave and reflected wave, you can get a standing wave, stationary wave. So waves have this phenomena called superposition. We never say particles superimpose. Particles collide. We never say waves collide. We say waves get together, superimpose. In Sinhala we call adhisthapana. Right? So that is the nature. That's the nature of waves. The waves are distributed, not localized. So waves can superimpose depending on the conditions. So therefore, these fundamental particles also, when you come to electrons, photons, everything, you can have a superposition. When you superposition means they can be at a given time they can be in different states. But as soon as you try to observe it, it collapses to one state. But in between, you can be in different states. So that is the idea behind this the superposition. I mean, that also comes in quantum computing also, because when you come to small particles, as long as you don't observe them, they can be either several states. It's called superposition. Actually, it comes from waves. It's nothing else. As I told you, quantum mechanics is wave mechanics. The difference is normal waves. Even normal waves, there are modes. No, is a fundamental mode, overtones. So again, that discreteness is popped out there when you think of waves. So therefore, it is yes, what you have asked is true. When you come to small particles, they can exist at a given state at the same simultaneously. So it's little difficult to understand in our normal common sense, but that is true. So you can have different state, but maybe now even electrons in atom, we say that electrons can be in this state 90% of the time. At the same time, you can have 10% of the probability of having an electron in the other state. But when you observe, it's only in one state. So when you observe, it comes like the coin comes and falls onto the ground. It should be either tails or it can't be both. But as long as it is on air, it can be either tail or tail.
Thank you for using those very descriptive examples as well. So it's all starting to make a lot more sense now for me personally as well. Alright, sir. With that, we'll be moving on to our next segment about quantum entanglement. So, sir, this is essentially a very intriguing concept, as I've heard before, and within quantum mechanics as a whole. So, would you be able to break down what quantum entanglement is to us?
Actually, that is also a very peculiar phenomena that scientists have observed. When you think of to have a quantum entanglement, you should have either two or more. So you can't entangle with one person. Entangle means correlated, combined. They love each other. That's the idea. So scientists have found when they have found this in electrons or photons. Once you prepare a so-called entangled state, combined state, correlated state, they are like together. Even you take one particle far away from the other person, when you do something, when you do a change here, the other particle knows about it. So this is a very peculiar thing, still scientists have not understood really. Now Einstein also said this is a spooky action at a distance. Spooky means you can't explain, adbhut, right? But that has become a reality. So once you have entangled particles, it depends on, now you have to have property. Now electrons, you have spin, call this property spin. One electron can be spin up, other one is down. So when you make an entangled state and separate them even further, even to large distances, you can't define the state of one particle without the other person. Now if you measure this spin up, that is definitely down. You don't have to measure it. It's something like this. Now even in life, sometimes we feel that, now say if you love someone dearly, say you have a girlfriend or wife or whoever, even if you are far away, you feel each other. I don't know, sometimes people say like that, right? It's not quantum entanglement, but I am giving you a normal day-to-day life example. Sometimes the parents would have said, if something happens, say your loved one is in UK or far away, if something happens to that person, you feel it. How come? I don't know, right? So therefore, this is something like that. So when you come to these small particles, it won't happen to everybody. If you have to have an entangled state, combined, correlated, togetherness. So once you are together, you feel each other So that is called the entanglement. So scientists have baffled because of this. It means that the information is going, now according to normal physics that we know, you can't send information much more than the speed of light. Right? So whatever you send can't be more than the speed of light. So for some reason, these two people, they know each other, right? So if you do something to one person, other person feels it. So they are like correlated. So that is called the entangled state. Still, scientists have not understood how this happens. Maybe it's the communication. Some people say, no, it's not transformation of information. It's some connection between the two. Once you prepare the entangled state, then now some people even relate this to Buddhism. Now, when you die, it's karma. So, the karma in your past life is correlated with the karma in this life. So is that quantum entanglement? I don't know. I'm not expert in Buddhism. So sometimes you relate Buddhist philosophy also with this quantum mechanics, because quantum mechanics is a very, very philosophical subject. It goes with philosophy. It goes with reality. Because scientists have found quantum mechanics play a very vital role in understanding the real world, small things. So they have had a lot of success in the past. So if you want to become a scientist, if you want to become an engineer, you don't need quantum mechanics much, unless you become a nanotechnologist or material scientist. If you're working with machines, generators, dynamos, you don't need quantum mechanics, right? But if you want to really work on fundamental studies, these ideas are very, very important.
Alright, so in that case, in your personal opinion, what do you feel like the practical uses of quantum entanglement?
Quantum entanglement has a lot of practical applications. So far, scientists have not really came into real practice. Now, there's something called quantum cryptography. Cryptography means, say you send a signal to some person. Say sometimes you send a secret signal, because this will be useful in this data communication and all this. Say some person is far away, you send a signal, say it's coded, and he has to decode it to understand. But in now, anybody can interfere with this, because third person comes and change the state. Now, if you have the entangled state, as soon as you try to change it, other person feel it. Oh, this has some intruder has get into this message. So that is one of the examples, because they are all correlated. No? If you measure this, that is already determined, right? So if you try to change in the middle, then the other person will get to know it. So that is one of the things. The other thing is now that is how sometimes useful in quantum. Now quantum computing means, now in normal computers we use electronic bits, either 0 or 1. If you have 2 bits, you can have either 0, 0, 0, 1, 1, 0 and 1, 1. But in quantum states, they are all, as I told, they are superimposed. So you can store data in more ways than what you think of in the normal bits, right? So therefore, quantum computers, actually scientists have day-to-day life, we don't need quantum computers. It's all type a letter, right? Quantum computers are very useful in doing very complex calculations, because it takes a lot of time using normal bits, because the description or the distribution of bits are very limited. Either you are 1 or 0, nothing in between. Like. So if you can do more operations in a given second, you can solve very difficult mathematical or other problem in a very short time. So that is the advantage of a now people always think, I can buy a quantum computer. It's useless. So day-to-day life work, you need it. But there are things that you have to do, say some complex mathematical problem or engineering problem, even economics, right? So sometimes the normal computers will take years and years, because they have to think of all the parts, because they can do only what at a time. Right? Now when you have superimposed positions, it can do faster. So that those are one of the major sort of advancement in the world that scientists are thinking of. Some have successfully made quantum computers, but they have not normal practical uses yet. Because when you think of these small particles, it's very difficult to keep them in one state. That's the difficult. Nature is always like that. Nature has always pros and cons. So you have to have either cool system, because if you take an electron spin won't be like this all the time. So you have to have some external conditions to occupy that state within itself, because things will change abruptly. So, but they have tried, they had been successful. So maybe in future, I don't know, maybe 10 years, 20 years time, quantum computers will be available. But again, that's for this basic, not for basic calculations or anything like that. It's useless to use that. But for advanced, to do advanced things, now you are talking about AI, artificial intelligence, data communication, things have changed now. If you ask me those things when I was young, I never had a clue about it. So things are changing very fast in this world. You have to learn so many things. That was very difficult, right? When we were young, we had very little things to study. So now you have, if you are working with computers, you have to refresh your knowledge every day. Sometimes I tell my physics students, doing physics is easy because our theories are very rigid. So if you know your physics now, you can even live with that physics till you die. But if you are a computer scientist, you have to always learn. Every day you have to learn, because things are changing so fast, even you can't cope up with it.
Welcome to NCHS.
Studying has never felt this good.
It's not just studying.
This is what a lab should be. Whatever I want, whenever I need.
I don't miss a single class of it.
I'm flying to Australia next week.
Commence degree pathways at NCHS and continue in Australia, Malaysia or USA. Unlock your future.
Thank you, sir, for describing what these uses are and what quantum entanglement is. And it truly is fascinating to see how fast the world has changed and how technology has taken over our daily lifestyles. And it's very interesting to see how we can obviously use some of these quantum computers if needed to in the future as well.
Yeah.
But with the discussion of those topics, sir, now that we have a rough idea about what quantum entanglement, quantum energy overall is, we'll be moving on to a really short break, and after that break we'll come back to discuss about nuclear physics and that topic as well. So now we'll be moving on to a short 5-minute break, and with that, break starts now.
Okay, thank you.
Ladies and gentlemen, welcome back to QuantumCast'24, where we are today here discussing about quantum mechanics and nuclear physics. Today with us, we have had a very interesting individual, Professor S.R.D. Rosa, a member of the management board of the Sri Lankan Atomic Energy Board, and it's been very interesting to have him discuss theories and overall give us very intriguing examples and concepts about quantum mechanics for now. So sir, now that we've wrapped up sessions about quantum entanglement and quantum physics, we'll be moving on to a short introduction to what nuclear physics is. So sir, if we're talking about nuclear physics now, would you be able to give us a rough overview of what this field focuses on, sir? Nuclear physics.
Actually, now nuclear physics started because atoms have nuclei. If you don't have nuclei, there's no nuclear physics. So scientists have started understanding the atom first, right? We all know that. Then scientists knew that there's a nucleus in the atom, so they like that model very much, nucleus and electrons, because it's similar to a solar model. Always when scientists have similar models, they like very much. So then nucleus came into the picture in the latter part of 19th and 20th century. Now how do we know that nuclei exist? Because some nuclei emit things. That's also one way of understanding a person. Now, if you want to understand a person, either he has to give something out, right? Say from his nature, how he talks, how he smiles. Then we try to understand the person. Or the other way of doing it is try to smash him, right? Do something. Then how he reacts to that. So those are the two ways that we can understand a person. So nuclei, luckily, when you come to unstable nuclei, they emit radiation alpha, beta, gamma, and so on. So now after that, actually, people have used this radiation for better life, especially for medical fields. You know, when the discovery of X-rays changed the whole world, because before that nobody ever would have thought about seeing a bone inside the person unless you remove it and unless you do something. So like that, now we have a lot of medical ways or medical instruments to detect things inside. Because how do you can find out things inside? It has to emit something. Now I can see you because light comes onto you and get reflected back onto my eyes. So like that, using light we can't see inside, no, it won't come out. So the radiations are very good. So if you inject something to a patient, then the gamma rays are emitted. The gamma rays can be detected very efficiently. So this is how the simple medical anything, even angiograms or whatever, you have to inject a small radioactive dye. They emit. It's like a LED. Of course, not emit light, but it emits a radiation. So that you can catch them. So we can't see from a naked eye, but you know how to measure gamma rays, and gamma rays can be converted to pictures. So like that, the nuclear physics has developed immensely over the last century and even this century. So then the other, now even as in the Atomic Energy Board, we soon start a cyclotron facility, because you know we have PET scanners, especially for cancer detection. You know that cancer becomes a menace. Someone told me every day there are, I don't know, 500, 600 new cancer patients. So how to detect a cancer? So there's something called the PET scanner. PET scanner means you inject a beta plus emitter. You know, in radioactivity there are alpha emitters, beta emitters. Beta plus is a positron. Positron means the brother or sister of electron. So when the positron get into an electron, they annihilate. We call it, all the mass will be converted to energy. So in the PET scanners, they detect these gamma rays. So unfortunately, this radioactive pharmaceutical, you know, we have normal pharmaceuticals and radioactive pharmaceuticals. So radioactive pharmaceuticals, you have to produce them. Normally they won't be in natural world. So at the moment we get it from India. So the half-lives are very short, so we have to spend a lot of money. So now we have started the project. It has come to our last stage. We have given the agreements to the Attorney General. Once you get it, the first medical cyclotron will be, cyclotron is needed because cyclotrons are to accelerate protons. So when you bombard protons onto heavy water, you can make this fluorine-18, which is a beta plus emitter. So like that, there are a lot of radiopharmaceuticals. Now if you have a prostate gland cancer, there's a separate isotope you need. So you know, scientists and medical people have got together. If science didn't develop, medicine will never develop. With all the medical equipments and everything, the root cause or the basic fundamental is in science, chemistry plus physics. So then the other one is actually nuclear power. You know, once nuclear fission, again scientists have found accidentally, scientists never thought that you can break a nucleus. Even great Rutherford said, if someone is breaking a nucleus, he is talking nonsense. But scientists have found that nuclei also can break. Once you break, you get enormous amount of heat. Because why that? Because the nuclei are very bound together. Now, if you love someone, if you are bound together, if you break the bond, what happens? You cry a lot because your bond is very strong, right? So nuclei are bound very strongly. So if you break the bond, you get enormous amount of energy. So that is the idea behind the nuclear power. You use that heat to generate steam using water. So we have embarked on that also, as well as Atomic Energy Board, because you know, in future, according to this climate change and carbon dioxide emission and carbon footprint, now world want to get rid of natural fossil fuels, burning natural fossil fuels, because that emit carbon dioxide. So world is always now go for renewables plus nuclear. So like that, we can always, science means what? Using science, we try to manage science and use scientific principles for the betterment of people. Of course, you can use it for to destroy people also. That has nothing to do with the sciences. It's not something wrong in sciences, it's something wrong with humans. Right? So therefore, there are so many advancement and useful applications in nuclear physics, because nuclei also play a vital role in atom. So if nuclei did not emit anything, we are deaf and dumb because we don't know what is happening. So luckily they are emitting. So emission is good actually. If you don't talk, if you don't smile, how can your friend can understand you? Because you look like this, you are deaf and dumb. So because you smile, because you talk, because you shout, we know you are someone like this, right? So nuclei luckily emit things. So those things we can use it for better life, especially all medical equipments. These CAT scans, CT scans, PET scans, of course using X-rays, people use a lot. So there are a lot of advancement in sciences. So in future there will be more. So I think as science students, you have ample things to learn from life. Maybe you all can do research and find out new things in life, So that I invite you all to go through with this fascinating world of sciences, because when you go through them, you enjoy things also. So therefore, that's the difference between doing any other subjects and science. Because science is always interesting, keeps on changing, right? So there are a lot of applications coming into the world. So therefore, you tend to you feel that you have done something to the world. So therefore, thank you very much for inviting me, and I hope you all understood something. So once again, thanks.
Welcome to NCHS.
Studying has never felt this good.
It's not just studying.
This is what a lab should be. Whatever I want, whenever I need.
I don't miss a single class of it.
I'm flying to Australia next week.
Commence degree pathways at NCHS and continue in Australia, Malaysia or USA. Unlock your future.
Thank you so much, sir, for joining with us on this session today. And with us covering majority of the topics that we had for today, and since we have a rough idea about how the future of quantum mechanics is going to look like, we'll start with wrapping up the session for today. So now, Professor Rosa, thank you so much for joining with us today and sharing all of your experience, expertise, and so many interesting and intriguing new concepts to all of our listeners. I'm 100% sure that everyone that's here listening has learned something new and has inculcated something that's useful for their lives, including myself really, because I learned a lot today. So thank you so much, sir, for sharing your career journey and what you have learned throughout your years. So sir, would you like to share any final thoughts with our listeners today before we move on?
Yeah, I think most of the students, they are the one who are listening to this type of thing. So it's very, very good to sort of have this type of sessions, right? You invite different people from different fields. You have to learn now. Still, I also know very little. I learn from others. Even I learn from students. If you want to get things done using IT and computers, we are not the experts. Because when we were young, we never had computers. Even we never had a phone at home. So therefore, it's a very fascinating world. Things are changing so fast. And my final advice is to all of you, as I told you at the beginning, try to enjoy life. Because we enjoy life by doing good things, not by doing bad things. By doing bad things also you can enjoy, but those enjoyments are very timely limited. But if you do something good, you enjoy by yourself. So learning should be a habit of enjoyment. Always I tell this, if you work out a problem and if you got it right, you should feel it. If you don't feel it, you don't love this subject, right? So love your subjects, whatever you do in your life, physics, chemistry. Maybe you like one subject more than the other. That is all right, because that's also nature, no? Everybody don't like the same subject. Then there's no advancement in life. So whatever you do in your life, try to behave yourselves doing good things. help others, work together, enjoy together, smile together, right? Work together, look at girls together. So it's all right, nothing wrong in looking at girls. I mean, if you are a boy, you have to look at the girls. No religions have told not to look at girls. So what you have to know your limits. That's what human beings are. We are not animals, no? We know our limits. So try to be simple as, right? You don't. There's nothing to be proud. Right? Whatever you do with your wholeheartedly, and enjoy the life.
Thank you so much, sir, for sharing all of those insightful experiences and all the words that you had to share with our viewers and everyone that's here in the backstage as well. Thank you so much, sir, for taking time off your busy schedule. And of course, thank you to all of our listeners for tuning in and wanting to learn something new. With that, ladies and gentlemen, join with us in our next episode for more fascinating episodes of QuantumCast. Today we discussed what quantum relativity and theories regarding quantum mechanics and nuclear physics are. In that note, ladies and gentlemen, until next time, keep exploring, stay curious, and of course, enjoy yourself no matter what you do. So thank you, sir, for joining with us. Thank you, viewers. That's it for today.
Thank you.